Welcome to Study Loop.
Hi everybody, thanks for joining me today. What we're going to be looking at is the concept of work and energy. And what we have is we have two blocks that are attached to a spring. So we have this 3 kg block sitting on top of a 2 kg block, which is attached to this spring shown here, and that spring is fixed to the ground at this end. What we're given is that the mass of the top block is 3 kilograms, the mass of the bottom block is 2 kilograms, and the spring constant is 40 newtons per meter. What we're asked to find is once the top block, which has a mass of 3 kilograms, is removed, what is the maximum velocity of the 2 kg block and the maximum height attained by that 2 kg block. So the first thing we're going to do, as always, is draw a free body diagram, and we're going to draw a free body diagram up the block, which we're going to use to create the force of the spring. So here is the 2 kg block, and as you know, that block is getting weighed down from the block by above and pushed up by the spring from below. So what we're going to have here is we're going to have a weight force from the block itself, and we're also going to have a normal force. I'm just going to draw it here, from the block above, and we're also going to have a spring force from the spring below. I'm just going to call that Kx. So as you can see here, that the two forces that are acting downwards, we can sum them up to say that the weight of the block plus the normal force from the block above is simply just the weight of both of these blocks. So I'm just going to write that as 5 times g, which is just the mass of each block combined, times gravity. And by Newton's third law, what we can do is actually draw the free body diagram for the spring as well in terms that make it a little bit easier to understand. So remember that Newton's third law is that every force has an equal and opposite force. So if we draw this from the perspective of the spring, we can see now that the normal force and weight force that are from the weight of the 2 kg block and the normal force from the 3 kg block can now be shown in the vertical direction acting on the spring. So that's normal W. And the spring force is acting in the downward direction, Kx. And the reason why we do this is this allows us to create and develop an expression for the force of the spring, which I'm going to call Fs. And given this free body diagram here, we can write this as Fs equals 5g, remember that is the sum of n plus w, minus Kx. So now we're going to use the idea of work and kinetic energy to solve for velocities. And what we're going to do is we know that the kinetic energy in the beginning is 0 because everything is at rest. And the kinetic energy of our block is simply 1/2 mv squared. Now, the work, we actually have two components that are contributing to the work done on this block, and that is the spring force and also the force of gravity on the block itself. Right? So U12 is actually going to be the integral of Fs, which is the spring force acting over a distance x, minus 2gx. And remember, 2gx is the work done by gravity of the 2 kg block over that distance x. So we know what Fs is, and what we're going to do is we're going to plug in for Fs and solve for this integral. So what this is going to do for us is we're solving this integral here. Plugging in for Fs gives us 5g minus kx. We're solving that dx minus 2gx. So following this, solving this integral gives us 5gx minus kx squared over 2 minus 2gx, which is equal to 3gx minus 20x squared. And we're doing 20x squared because if you recall, k is 40 newtons per meter. 40 divided by 2 is 20. So this gives us the expression for U1 to 2. Now plugging this into our equation for kinetic energy and work, we know, as you might recall, T1 plus U from 1 to 2 is equal to T2. We know that T1 is actually 0. T2 is 1/2 mv squared. Remember that the mass is actually 2 kilograms, so this simplifies down to simply v squared. So what we're left with the final equation is 3gx minus 20x squared equals v squared. Now, since these blocks are connected, we know that the maximum velocity occurs when the derivative of velocity with respect to x is 0. Now, we do have the expression here is actually in terms of v squared, but that's okay, because the idea of the maximum velocity occurring at the maximum position still holds, because we know that by maximizing this expression on this side, we'll maximize the expression for velocity squared, because all we're doing at the end is simply taking the square root of velocity squared to get v. So I am just going to call this equal to f, and just to make this mathematically correct, we're just going to say when df dx is equal to 0. Right, so taking the derivative of df dx, what we get is df dx equals 3g minus 40x. And by setting this equal to 0, we know that the x at which we have the maximum v is 3g over 40 meters. And, as I said before, maximizing the expression on the left is going to maximize our v squared, which is going to maximize our v. So what this ends up being is that our x squared max v is equal to 0.7358 meters. Plugging this into our equation for v, we get a v squared of 10.82, which results in a maximum v max equal to 3.29 meters per second. And that is our final answer. Now remember, we're also asked to solve for maximum height that this block 2 reaches. So we know that just due to the principles of energy, the maximum height that we're going to reach is when the velocity is 0. So remember that maximum height occurs when velocity is 0. We know that the system is starting from rest, so T1 is equal to 0. Similarly, maximum height occurs when kinetic energy is 0, so T3 is also equal to 0. So all we're really looking at is the work part of this equation. So the equation that we're going to use for work is very similar to the equation that we used before. The force of the spring is actually the same, right? We're just integrating to h because we know we want to solve for that maximum height. So we're going to do 5g minus kx, all this to dx, minus 2gh, remember, which is the work done by gravity. And we solve this integral and we get 5gh minus 20h squared, remember, because k is 40 newtons per meter, minus 2gh. So simplifying and combining terms, 3gh minus 20h squared equals u1 to 3. Remember that T1 and T3 are 0, so this expression actually is going to be 0, equal to 0 when we plug everything into the work kinetic energy relation. And this is a simple quadratic equation, and by solving this quadratic equation we get two results of h equal to 0, which obviously is wrong in this context, or we get h equal to 3g over 20, which is the answer we're looking for, which is equal to 1.472 meters. And that is our h max.